On behalf of the International Replication Repair Deficiency Consortium, we'd like to thank you again for joining this educational seminar. Today, I'll be introducing to you a new diagnostic tool that we're working on. Just as Dr. Durno had alluded to, detecting replication repair deficiency is super important, especially early on, potentially even before cancer. So I'll be talking about that. Just to give you a little bit of background, I guess, this is a collaborative work from all over the world. We have Dr. Marufka here, who's a collaborator with us from Boston and now Israel, and also Lejane, who is now taking over my work as I am wrapping up my PhD. But again, to reiterate the issue of what we're working on and why we're working on a diagnostic tool, that the current problem of replication repair deficiency is it exists in many cancers, but we do not, or sometimes we cannot look for it fast enough. So we miss many cases with the syndrome, and we're trying to tackle this problem using a new tool, which we call Logic. But before I get to how exactly that works, I want to recapitulate a little bit of how the replication repair works. So as the DNA is replicated by the DNA polymerase, it makes some mistakes, which are repaired by the mismatch repair system, as well as the innate or intrinsic activity of the proofreading domain of the polymerases themselves. And Dr. Das explained a lot about what mismatches are, and I will be focusing on how logic is based on microsatellite insertions or deletions. So what are microsatellite insertion deletions? Microsatellites are repeat regions in the DNA. They have the same, like Dr. Das said, the same alphabet repeated multiple times. In this example, I have 10 A's. And they can be stable, so they don't change their length of the A's. However, they can also get these mutations called insertions and or deletions, where the bases are physically added or deleted from the original 10 or whatever length they started off with. And this is something that's very well known, is that the mismatch repair system, the 4 genes I showed just earlier, are responsible for correcting these microsatellite insertions and deletions to make it stable. And so there is a currently used clinical tool using 5 microsatellites in the genome to detect whether they have microsatellite insertions or deletions, to basically infer that they have mismatch repair deficiency if there are insertion deletions. But interestingly, there are actually 23 million microsatellites that exist all throughout the genome. But again, as I said, the current tool, which is also called the Promega panel, uses 5 microsatellites. It's very cheap, it's very fast. So we thought that maybe that could be used to detect mismatch repair deficiency in children, particularly in cases with CMMRD. However, when we used that tool, we actually found that most of the cases were missed for mismatch repair deficiency. Here in dark blue, we show here that there's only 18% out of 96 cancers that were tested that had detectable microsatellite indels, or microsatellite instability, also called. And interestingly, because children with mismatch repair deficiency have it in all their cells, we thought that even their normal or non-malignant tissues would have microsatellite instability, in which case we did not find any. So this biologically doesn't make sense because we know mismatch repair fixes or corrects microsatellite indels. But we thought that maybe that with just using the 5 loci is not enough to detect what's really going on in these cells. So we took a new tool and we detected all 23 million microsatellites that exist in the genome. And indeed, we did where we were able to find the mismatch repair deficiency or the microsatellite indels in childhood cancers with replication repair deficiency. So in green, these box plots are showing the number of microsatellite indels that exist in the genome. And in green, we have wild types, so they have mismatch repair activity, fixing these microsatellite indels and therefore are low. However, in red, we have cancers that are from children with mismatch repair deficiency that have increased number of microsatellite indels, comparable or similar level to the adulthood cancers which have microsatellite instability with the Omega panel. Another very interesting fact about these microsatellite indels is that they were actually not all random. And they indeed, in fact, depended on whether they had mismatch repair deficiency or the other side of replication repair, which is polymerase proofreading deficiency. So we found that in these cancers, when they had a lack of mismatch repair, they actually were enriched here and shown in deep dark red for -1 deletion in the microsatellite. Here on the y-axis is the size of the microsatellite indel, and below the 0 are deletions, and above the 0 are insertions. So in mismatch repair deficient tumors, a lot of -1 deletions. On the other side here, when we have no polymerase proofreading, we found that these microsatellites were enriched for +1 insertions, as shown in the red here. So this is really the biological basis of what our tool called Logic is coming out of. That we can actually attribute the number, or we can attribute and count the number of microsatellite deletions or insertions to determine what kind of replication repair deficiency that an individual cancer has. Here on the left, I'm showing the summary data for all the cancers that we tested initially for using this tool. So in green, we have, again, the mismatch repair wild type. So they have replication repair to fix the indels, and they have low scores of both. And in CMMRD cancers, which have mismatch repair deficiency, they have high score of -1 deletions. Polymerase have higher scores of the insertions. And cancers that have both polymerase and mismatch repair deficiency have high scores of both, which has important therapeutic implications, specifically for immunotherapy, which Dr. Das just talked about. And I will show you how that relates to in a slide. And so in order to go back to the problem of how this tool can be used to diagnose or detect replication repair deficiency, we use cancers that we screen regularly for this at the kids in Toronto. And we found four cancers that had high scores of the -1 deletions in these tumors. And we missed these cases initially, but through this test, we were able to find that these 4 cancers actually originated from Lynch syndrome, which many of you may know is the heterozygous germline deficiency of the mismatch repair activity. So this tool was able to diagnose or detect mismatch repair deficiency in cancers that were not suspected of having it before. Now for therapeutic implications, I mentioned a little briefly that the score had therapeutic implications. And the Polina score, which again is the +1 insertion, was able to actually predict better survival on patients with immunotherapy. Dr. Das explained a lot about why or how this could happen, but just briefly, the Polinas or the +1 insertions may be responsible or may be connected to having a lot of the tumor mutational burden, as well as higher MS indels or MS insertions, which can trigger an immune response in these tumors. So everything I showed you so far was very encouraging, but it used expensive whole genome sequencing, which really isn't available all throughout the world and really can't be implemented very easily. So what we really need is a tool, which we call Logic, that is robust and cheap and can be quickly implemented into every center across the world. So in order to do that, we wanted to first compare the efficiency and the effectiveness of Logic as a tool in detecting mismatch repair deficiency in tumors. So here we tested on the right side, I just want to direct your attention here, is when we used Logic on 56 tumors, we found that we were able to detect mismatch repair deficiency in 100% of the cases. And on the left, this is the ProMega panel, which is actually the 5 microsatellites that I showed before, again, showing that there's only a 14% sensitivity in detecting it. And TMB, which Dr. Das mentioned, and there's another tool called immunohistochemistry, which are both very good tools that are currently used routinely in the clinic. However, Logic seems for the data shows that Logic has better sensitivity than these two. So this, again, was very encouraging for us that Logic can be used as a tool to detect mismatch repair deficiency in the tumor. But we know that CMMRD is a condition that ablates mismatch repair activity in all their cells. So we thought that maybe we can use the 23 million microsatellites to detect mismatch repair deficiency just using blood DNA. So again, just to show you, this is the MMRD score again, counting the deletions. We were able to find that CMMRD individuals had a significantly increased score of MMRD score than all the other cancer predisposition syndromes that we tested. These are actually related to replication repair, but they were shown to be low, and other to a pediatric cancer predisposition syndrome. So this shows that this tool that we have can detect CMMRD just using blood tests. And one thing I would like to allude to later is the big range of the CMMRD, MMRD scores, which we think that could actually predict progression of the tumor, which I'll get to in a few slides. But in order to even increase the feasibility of this tool, so to make it even more non-invasive, we tested actually saliva DNA from cases from all over the world actually. And we were able to find that CMMRD individuals had increased MMRDness scores, just even using saliva compared to the control. So this was a pilot study that was conducted, and we are openly requesting for more samples. So if you'd like to collaborate with us on this project, please do contact us after. So this shows how even a non-invasive test like saliva can detect CMMRD in these individuals. And one other problem that we wanted to address using logic was, well, it's related to surveillance actually, as we alluded to a couple of times here and there. Just to reiterate, full surveillance does increase survival very significantly compared to the no surveillance. However, the surveillance regime or protocol actually involves a lot of frequent hospital visits, a lot of MRIs, and that actually can be quite burdensome for patients. So we thought maybe logic can be used as a tool, as you saw the big range in the MMRDness scores in the blood, could be actually used to see if the surveillance can be modified for patients who may not need it right at the onset, for example, in infants, this is very intensive for them. So on the y-axis here, we have in the consortium data that we have on the age of cancer diagnosis. And on the x-axis, we have low MMRDness score to increasingly high MMRDness score, where we have high MMRDness scores actually correlated to younger age or earlier onset of cancer. And on the flip side, we have patients with low MMRDness scores that showed that they had older cancer diagnosis, older age of cancer diagnosis. And when we now plot every individual on the flip scale, where we have on the right here, where we have old age of diagnosis now on the x-axis, below a certain level of MMRDness, the earliest cancer onset for these individuals was at 19 years old. So potentially what we can do now instead with this MMRDness tool is by taking blood tests, we can actually say or determine that a young patient with a score that's lower than this, so let's say they're 10 years old, may not have to be put on surveillance immediately, but instead undergo routine blood tests to see if their aggressive or risk of cancer increases over time. And that could potentially curb the patient burden for monitoring for surveillance. So now to summarize, why are we so excited and what is logic used for? First, it can be used for diagnosis of replication repair deficiency in cancer, predict response to immunotherapy. We can diagnose it in the blood or saliva, and it can determine the initiation of surveillance. So these are the things that we are currently working on, and what is going on now, what we're doing in Canada. First, in order to detect mismatch repair deficiency in Canada, what we have is we have multiple tests that involve multiple thousands of dollars, which are currently being used. On the other hand, if we're now able to replace this with logic, we will be able to actually save so much money. Actually, this test is $250 for each tumor, but really we can curb it even lower to $150 per test, which will make this test much easier to do all over the world. And I would like to highlight your attention to this is this would save Canada, the healthcare system in Canada, up to $15 million a year. It's an amazing tool that we could use that can really benefit, I think, society in general as well. And now what is my ultimate vision of what logic can do is we want to create a report for using logic for every single patient that would be suspected of this kind of, to have this syndrome. So first, I hope you're familiar by now with the MMRDness and poliness. We use that to actually determine their MMR or polymerase proofreading deficiency. And there are two aspects of this that are additional to this, which I didn't really talk about, but you know what tumor mutational burden is by Dr. Datta's talk. And basically tumor mutational burden and copy number variants are two very important biological and genetic testing or markers that can determine treatment efficacy of different drugs, and also what kind of tumor that they have using the copy number variants as potential indicators of that. But altogether, what we can have is a summary of each patient based on these 3 different tests, which are now all part of logic, and give recommendations on how they can be treated and how they can be monitored in the clinic. So this is what it would be possible with the full development of logic. So I'd like to thank you all so much for your attention, and thank you so much for your contribution and input. This project could definitely not have taken off without the consortium, without the input from everybody from all over the world.